How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You tap your phone, you open your banking app, you see your balance, precise to the cent. You scroll your social media feed, you see a photo from a friend, posted 3 seconds ago. You see an ad for shoes you were looking at yesterday. You go to an airline website, you search for a flight from New York to London 6 months from now under $500. In less than a second, you have a list. You click 1. Seat 7A, you enter your credit card number, a spinning wheel, and then confirmed. Your bank balance is now lower. Your airline profile shows a new trip, and in that exact same instant, thousands of other people searching for that same flight, they no longer see seat 7A. It's gone. It's yours. We do this dozens, hundreds of times a day. We move money, we create data, we claim digital property, and we just trust it. We trust that the balance is correct. We trust that the like was recorded. We trust that seat 7A is ours, and that the airline didn't accidentally sell it to 3 other people. We assume it all lives in the cloud or on some impossibly fast computer. But that's not an answer. That's just a new name for the magic. The real question is, how does this actually work? What is the fundamental, simple idea that allows for this shared, global, instantaneous memory? Today on First Principles, we are opening the most important black box in the modern world. It's not the microchip. It's not the internet. It's the system that runs on them. We are talking about the database. The world we live in is built on databases. They are the engine behind every bank, every hospital, every social network, every online store, every government, and every corporation. Without them, the entire digital economy, the entire modern world would simply stop. It would collapse into chaos. And yet, if you ask someone how it works, you'll probably get a shrug. Maybe it's like a giant Excel spreadsheet or a big folder of files. The truth is, it's nothing like that. The real story is far more clever, and it's built on a few simple, powerful principles that are designed to solve a problem that is much, much harder than just storing information. The problem is trust. So let's go back. Let's go back to a time before the database. What was the problem we were even trying to solve? Imagine it's 1965. You are a travel agent. A customer walks in and wants to book a flight from New York to London. You don't have a computer. You have a telephone. You call the airline. On the other end, an airline reservation agent answers. That agent has a book, a massive physical ledger. Or if they're high-tech, they have a big, rotating, Lazy Susan-style card catalog. Each flight is a card. Each card has a grid of seats. The agent finds the card for that flight, looks for an empty seat, and literally, with a pencil, writes your customer's name down. Now, what if 2 agents are trying to book the same seat at the same time? One agent in Boston and one in Chicago both call the central office. 2 reservation clerks walk over to the same spinning file. One gets there 3 seconds before the other. The person in Chicago gets the seat. The person in Boston is told, "Sorry, it's gone." The agent in Boston has to hang up, apologize to their customer, and start the whole process over. It was slow, it was clumsy, but more importantly, it was fragile. What if the agent made a mistake? What if they accidentally erased the wrong name? What if 2 agents did manage to write their name on the same line? What if the book was lost? What if there was a fire? This was the problem. It wasn't just, how do we store information? A text file can do that. A piece of paper can do that. The problem was, how do we store information so that many people can access it and change it, all at the exact same time, without it turning into a complete and total mess? How do we guarantee that the information is always correct, always consistent, and never lost? This is where the story usually jumps to computers. But the first, most important idea isn't about computers at all. It's about organization. In the 1960s, data was chaos. Early computer systems stored data in all sorts of custom formats. If you were a programmer, you had to know exactly how the data was laid out on the magnetic tape just to find a customer's name. Every new application had to reinvent the wheel. And it was brittle. If you changed anything about how the data was stored, every program that used it would break. Then, in 1970, a brilliant mathematician at IBM named Edgar Codd, or Ted Codd, published a paper. It was called A Relational Model of Data for Large Shared Databanks, and it was, in its own quiet way, as revolutionary as the invention of the microchip. Codd was a mathematician, not a programmer. He looked at this mess, and he proposed a single, elegant, and simple idea, the first principle. He said, "Stop thinking about how the data is stored on the disk. Stop worrying about tapes and pointers and file structures. Just stop. Instead, let's think about the data itself and the logical relationships between different pieces of data." He proposed that all data, any data, could be organized into simple tables, just like a spreadsheet. A table has columns, which define the type of data. For example, a "customers" table would have a customer ID column, a first name column, a last name column, and an address column. And it has rows. Each row is a single, unique record. Row 1 is customer 101, Alice Smith, 123 Main Street. Row 2 is customer 102, Bob Jones, 456 Oak Avenue. This seems obvious, right? So obvious it's almost trivial. But here is Codd's genius. He said, you don't just have one table, you have many simple tables. You have your "customers" table. You have a "flights" table with columns for flight number, origin, destination, and time. And then, here's the key. You have a "bookings" table. What's in this table? It's simple. Booking ID, customer ID, and flight number. This is the relational part. The "bookings" table doesn't contain all the customer's information. It doesn't repeat Alice Smith and 123 Main Street, it just contains the key, the customer ID 101, that points to the correct row in the "customers" table. It relates one table to another. This is the common misconception we need to clear up. A database is not just a giant spreadsheet. A single, giant spreadsheet is actually the problem. Imagine if our airline used one giant spreadsheet for all its bookings. The first row would be Alice Smith, 123 Main Street, New York to London. The next row, Bob Jones, 456 Oak Avenue, Chicago to Miami. Now what if Alice Smith books another flight? We add a new row, Alice Smith, 123 Main Street, New York to Paris. We've just repeated her name and address. This is called redundancy. And it's a disaster. Why? Because what if Alice moves? She calls in to update her address. The agent has to hunt through this entire giant spreadsheet and find every single flight she's ever booked and change the address on every single line. If they miss one, the data is now inconsistent. The database is lying. In Codd's relational model, this is simple. Alice calls. The agent goes to one table, the "customers" table, finds one row, customer 101, and changes the address one time. That's it, because all the "bookings" records only store her ID, 101, they are all automatically, instantly, pointing to the new correct address. This principle is called normalization. It's the art of breaking data down into its smallest, most logical, non-redundant parts. This single idea, storing data in simple, related tables, is the first principle of the modern database. It created an entire industry. You've heard the names: Oracle, MySQL, Postgres, Microsoft SQL Server. The SQL stands for Structured Query Language. It's the language we use to ask questions of these relational tables. But this elegant structure, Codd's relational model, it creates a new problem, a huge new problem. Let's go back to our customers table. It's clean. It's beautiful. It has one row for every customer. Now let's scale up. Our airline has 500 million customers. That's 500 million rows in the customers table. A customer, let's say his name is David, calls in. He gives you his email, david.lee@example.com. He wants to find his booking. The computer has this table. It's a file on a hard drive. How does it find David's row? Well, the simple brute force way is to just read the entire file. Start at row 1. Is the email david.lee@example.com? No row 2, is it? No row 3. No, it has to scan one by one through potentially 500 million rows until it finds him. This is called a full table scan. And even on a fast computer, it would take minutes, maybe hours. The website would time out. The customer would hang up. It's completely unworkable. So how does a database find one row out of 500 million in, say, a few milliseconds? This is the second principle. It's the magic trick that makes databases feel so fast, and it's an idea you already use every single day. You have a 1,000-page textbook on biology. I ask you to find the section on mitochondria. What do? You don't start on page 1 and read every word. That would be insane. You flip to the back of the book. You go to the index. You scan the MS, mitochondria, and right next to it, it says pp 245,250. You've just turned a multi-hore task into a 10-second one. A database does exactly the same thing. When a database designer creates a table, they have to think about how people will search for data. They'll say, I know people are going to search for customers by their email address. So they tell the database, please create an index on the email column. The database then does a bit of work. It creates a brand new, separate, hidden file. This file is the index, and it has two simple columns. One column contains every single email address from the customers table. The other column contains a pointer, a special address that says exactly where that customer's full row of data is stored on the hard drive. But here's the crucial part. This index file is sorted. It's sorted alphabetically by email address. So now when you search for david.lee@example.com, the database doesn't even look at the giant 500 million row customers table. It goes to the small, sorted email _index file. And because it's sorted, it can find david.lee@example.com almost instantly. It uses a clever algorithm called a binary search, which is like playing the high-low guessing game. It jumps to the middle of the index. M too high, jumps to the middle of the first half. F too high, C too low, D, and in a handful of steps it's there. It finds the entry, david.lee@example.com, and right next to it is the pointer, block 734, row 5. The database then takes that pointer, goes directly to that one specific spot on the hard drive, and plucks out David's full row of data, David Lee, 888 Pine Street, etc. It never scanned the other 499 million. 999,999 rows. It just jumped. This is the secret to database speed. It's not one big file. It's the main data files, plus a whole collection of highly optimized, sorted index files that act like a superfast table of contents. Of course, this is a trade-off. When you add a new customer, the database has to do a little extra work. It has to add their row to the main _customers table, and it has to add a new entry to the email_index and the _customer_rid_index and the _last_name_index. Writing new data becomes slightly slower. But in exchange, reading data becomes thousands, even millions of times faster. And for most applications like a website, you read data, looking at profiles, searching for flights, far more often than you write it. So now we have our two principles. 1. COD's relational model. Data is organized into simple, linked tables to ensure it's logical and non-redundant. 2. The index. We use sorted index files to find any piece of data almost instantly. This seems complete. We have an organized system. We have a fast system. Isn't this all we need? No. We are still missing the most important piece, the aha moment, the one principle that separates a database from a spreadsheet, the idea that allows us to trust it with our money. Let's go back to our flight booking, seat 7A. You click Confirm. What actually needs to happen in the database for this to be successful? Well, at least two things. First, the database needs to create a new row in the _bookings table. Booking Idaho, 90210, customer ID 101, flight number 42. This records that you now have a booking for that flight. Second, the database needs to go to the flights table. It needs to find the row for flight 42. It needs to find the seats available column. And it needs to change that number, subtracting 1. Let's say it goes from 150 available seats down to 149. So, two separate operations, a write to the bookings table, and an update to the flights table. Now, let's introduce our old enemy, chaos. What happens if the database server crashes, the power goes out, a hard drive fails? What if the database successfully does step 1, it adds your new booking, you're confirmed, but then, before it can do step 2, the power goes out. The server reboots, you check your profile, your booking is there, you're all set, but the database never updated the flights table. The flights table still says there are 150 seats available. The system is now in an inconsistent state. It is lying. It thinks you have a booking, but it also thinks your seat is still available. So what happens? The next person to search for that flight sees seat 7A as available, and they book it. And then another person books it. Now, 100 people show up at the gate for seat 7A. The airline has collapsed. The entire system of trust is broken. This cannot happen, ever. This is the problem that database engineers live and breathe. It's the problem of atomicity. To solve this, databases introduced the third and most profound first principle. It's an idea called the transaction. A database transaction is like a magic invisible box. When you click Confirm, the database doesn't just do step 1 and then step 2. Instead, it says, I am beginning a transaction. It puts both of those operations, the write and the update, inside this one conceptual box. This box comes with a terrifying, beautiful guarantee. It is atomic. Atom comes from the Greek atomos, meaning uncuttable or indivisible. An atomic transaction has only two possible outcomes. 1. All of the operations inside it succeed perfectly, or 2. None of them do. There is no in-between, there is no partial success, it is all or nothing. So let's run our crash scenario again. You click Confirm. The database begins the transaction. It performs step 1. It writes your new booking to the _bookings table. It moves to step 2. It tries to update the _flights table, and crash. The power goes out. The server reboots. The database software starts up, and the very first thing it does before anything else is look at its internal log. It sees that transaction 123 inches was started, but it never finished. It never got a commit signal. The database now knows that the data is in a potentially corrupt, inconsistent state. So what does it do? It performs a rollback. It goes back to step 1. It finds that new row in the _bookings table that it wrote, and it deletes it. It undoes everything that happened inside that failed transaction. It puts the database back into the exact state it was in before you clicked the button. So what happens to you, the user? You get an error message. Sorry, something went wrong. Please try again. You might be annoyed. You have to click the button again, but think about what didn't happen. The database did not lie. Seat 7A was not double booked. The system's integrity is intact. You click again. This time, the transaction completes. Step 1 succeeds. Step 2 succeeds. The database writes commit to its log, and only then does it flash confirmed on your screen. Now, you know that your booking is real and that the seat count has been reduced. The data is consistent. This all-or-nothing guarantee. This is the unseen giant. This one idea, the atomic transaction, is the bedrock of our entire global economy. It's not just one idea either. It's a set of 4 promises, a contract, that a database makes with you. It's known by the acronym ACID. A stands for atomicity. This is what we just talked about, all or nothing. C stands for consistency. This means the database promises to never allow itself to enter an inconsistent state. Before a transaction starts, the database is consistent. After it's over, it must be consistent again. If you tried to book a flight that doesn't exist, the transaction would fail the consistency check and be rejected. If you try to transfer money from an account with a 0 balance, the transaction is rejected. It enforces the rules of the data. I stands for isolation. This is the really clever one. It solves the 2 agents, 1 seat problem. Isolation guarantees that even if thousands of people are using the database at the same time, every single transaction will feel like it's the only thing happening in the entire world. When your transaction to book seat 7A begins, the database places a lock on that row in the _flights table. If, in that same millisecond, someone else tries to book that same flight, their transaction waits. It's put in a queue. It is isolated from your transaction. It can't even see the change you're in the middle of making. Only after your transaction commits, after you've successfully booked the seat and the seat count is reduced, is the lock released. Then, the next person's transaction is allowed to run. It now reads the new data, sees the seat count is lower, and continues. No 2 transactions can ever trample each other. And finally, D stands for durability. This is the simplest, most comforting promise. Once a transaction is committed, it is permanent. It will survive a power failure, a server crash, anything. The database writes the change to a permanent log, like a plane's black box, before it even tells you confirmed. So if the server crashes 1 millisecond after you get that confirmation, the database will use that log to restore your change when it reboots. It's durable. Atomicity, consistency, isolation, durability, ACID. This set of guarantees is the real first principle of a database. It's not a file cabinet. It's not a spreadsheet. It's a high-stakes, high-concurrency transaction processing system. It's an engine for trust. COD's relational model gave us organization. The index gave us speed, but ACID gave us integrity, and that changed everything. That's why we can have global banking, real-time logistics, and instant flight bookings. For decades, this was the entire story. The world ran on these powerful, reliable, ACID-compliant relational databases. They were, and still are, fantastic for structured data, bank accounts, customer lists, flight inventories, things that fit neatly into tables. But then, the Internet changed. In the mid-2000s, a new problem emerged, the problem of scale. Companies like Google, Amazon, and the brand new Facebook were dealing with a new kind of data. It wasn't small, structured, transactional data like a bank transfer. It was a tsunami of messy, unstructured data. Billions of status updates, trillions of likes, petabytes of photos, web pages, user comments. For this kind of big data, the rigid structure of a relational database was limiting. You didn't always know what the columns would be, and more importantly, you didn't always need the ironclad perfect guarantees of ACID. If you like a photo and I'm on the other side of the world, does it matter if I see that like this exact millisecond or in 2 seconds? Does it matter if, for a brief moment, the like counter is off by 1? No, it's not a bank transfer. The integrity of the system is not at stake. What mattered was speed and scale. They needed to be able to absorb millions of writes per second and spread that data across thousands of cheap computers all over the world. This led to the rise of a new breed of databases. We call them NoSQL, which doesn't mean no to SQL, but not only SQL. These databases made a deliberate, conscious trade-off. They decided to relax some of the strict ACID guarantees, especially consistency and isolation, in exchange for mind-boggling speed and horizontal scale. Instead of perfect, immediate consistency, they offer something called eventual consistency. When you upload a video, it might take a few seconds or even minutes for it to be visible to all your friends around the world. But it will get there, eventually. This is a different tool for a different job. You would never run a bank on a NoSQL database, and you would never try to run Facebook's social graph on a traditional relational database. The world now needs both. So, where does this leave us? We started with a simple magical tap on a screen, a bank balance that just is. And we deconstructed it. We found it's not magic at all. It's a series of incredibly clever solutions to very hard problems. We found that the first principle isn't just storing data. That's the easy part. The first principle is organization, COD's relational model, which turns data chaos into clean, logical, related tables. The second principle is speed, the index, which acts like a book's table of contents, allowing us to find one needle in a stack of a billion haystacks almost instantly. And the final, most important principle is trust, the acid transaction, the all-or-nothing, atomic guarantee that our data will never be corrupt, never be inconsistent, and never be lost. A promise kept in milliseconds, trillions of times a day. The database is the invisible, sleepless, obsessive-compulsive librarian for all of humanity. It's the traffic cop managing rush hour for every piece of information on Earth. It is the engine of our collective memory. The next time you tap your phone and the world responds exactly as you expect, remember that you are not just accessing a file, you are participating in a transaction. You are placing your trust in a system of guarantees written 4 decades ago that quietly and perfectly holds our entire complex digital world together.
You've been listening to First Principles. Until next time, stay curious.